in listen-only mode.
Hi everybody, welcome to the seminar on beams. This is our sneaky, simple, and complex element. I'm Kyle Hamilton, the staff engineer here at Predictive Engineering. Pretty soon we're going to have our senior staff engineer, Adrian Jensen, joining us to answer questions and be manning the keyboards here. I've also got our account manager, Eric, and I'll let him share a few words before we jump into our beam elements.
Good morning, everyone. I just wanted to go over real quick what Applied CAX can do for you, as for those of you who aren't already clients and have experienced our superior technical support from Adrian, George, and Kyle. We're all about making sure our clients are utilizing Femap and a variety of Nastran solvers to their full capabilities. If there's any issues, the FEA engineers who are not application engineers, I remind you, are here to respond to support questions. There's no ticketing systems. There's no bouncing around the world, lengthy delays. They are on it in short order. In terms of those of you who are not clients, moving maintenance to us actually costs you nothing, other than, of course, lost engineering hours from lack of or poor technical support from perhaps your current provider. In terms of going down the road to training-wise, we've got a training class coming up in October, from October 10th to the 14th here in the ever sunny Portland, Oregon. Adrian teaches this class twice a year, can go to remote locations as well, and it's a great opportunity for, as we like to call, organic learning opportunities for newer users of Femap, or simply those who want to gain proficiency. It's a great hands-on experience, and we attached a review here from Stan, who actually flew all the way over from Belgium here in April to participate in the Femap training class. You can see other reviews online. It speaks for itself. It's truly an outstanding class. If you're interested in either the class, maintenance switch, or any other questions, we can help you out with your capabilities. Feel free to give me a call. There's my phone number there. My email's there. And as you can see from the picture, it's one of my good friends, Lucy. And perhaps I'll have some fishing intel to share with you in the process. All right, I'll turn it back over to the beam master, Kyle, here.
All right, thanks, Eric. So let's go ahead and get rolling in here. A quick overview of what we're going to be talking about. In the beginning, we're going to start off with some simple models, beam nomenclature, beam, what all of the terminology means, how beams work. And we're really going to be looking at simple cantilever beams. As we move through, we're going to go on to bolted connections, some APIs, some post-processing, exporting beam and shear forces to data tables, and then we're going to be moving on to some Freebody diagrams and releases, and using beams as linkages even. So if you're a new user, this should be great from the beginning. If you're a more experienced user, you'll definitely, it might be a little slow in the beginning, but you'll definitely get some useful information towards the middle and end here. So first up, intro to beams. I pulled some text out of the Nastran theoretical manual. And beams are very simple, but they also can be extremely complex, and really you can have problems sneak up on you. They even say that the versatility of the beam is the cause of the difficulty. And they're very useful, but you really need to know what the limitations are and what you're doing with them. So beam elements, just to start off, we have 6 degrees of freedom at each end, translation in 3 directions, and rotation about the 3 axes. We've got each beam element has its own local axis system. So no matter what the orientation of your beam is in space relative to your model axis system, the x direction is always going to run down the length of the beam, and you're actually going to define your y direction. When we look at our Femap interface, they have a couple different terms that can be kind of confusing at first. They have beam end A and beam end B. Beam end A is the first node that you're selecting when you create your beam. End B is the second node. we'll get into how to tell which end is A and B later on in the seminar. You have plane 1, plane 2. Those correspond to your axes or your planes through your beams. And then one of the terms you'll also see is combined stress. And that's going to be the sum of your axial stress down the beam, your shear and bending stress. And it's important to note that the torque is not included in that. So we'll get into that a little bit more in a second. Real quickly, beam mesh. Now, you may have heard that beams are exact elements and that you only need one element to have an accurate beam. And that is true. And it's important to note that there are some limitations to that. If let's say you have a cantilever beam like this one here, it's fixed on the left, force in the y direction on the right. You'll see if we plot translation here and compare that to a 10 element beam, the mesh density doesn't change our max deflection at all. And so the deflection at the end is going to be the same. The stresses at the end are going to be the same, the maximum stress in the beam. And that is important to know. But this does have some situations where you do want to use more than one beam element, such as if we're looking at intermediate stresses in the beam, you'll see that the deflection is different throughout the beam. And also, when we go into our vibration of beams, if you have a simply supported beam such as this one here, even or with one element, it won't even show you any normal modes. It'll tell you it's over-constrained. But as we get into our two elements, you can see there's all you can really capture is the vibration and the arcing direction here with one arc, but you really miss out on all of these different mode shapes throughout the beam. So if you're looking at vibration, definitely play around with increasing your mesh density, and you will have a little bit better results. So let's go ahead and jump into our Femap interface. We've got a model a little bit started here. We'll model up a cantilever beam and look at some stresses. So I've already got my material. I've already got a couple nodes to make it a little quicker here. The next step here is to create our beam property. And we'll just choose our beam. All right, so we've got our beam definition interface. I'm going to go ahead and pick this aluminum material. Go down here to our shape dialog. And this is one of the things that changed in 11.3. We've got a little bit more descriptive dialog box, height and width. I'm going to go ahead and make a 2¼ inch tall and 2 inch wide beam. And you'll notice as soon as I tabbed out of the height and width definition box, it's showing this, or updated the image over here. We've got the center of mass of our beam. We've got our these 4 points on the sides. These are our stress recovery points. When Femap's calculating the stresses in the beams, you're not getting stresses like full field stresses by default in the results. You're getting stresses calculated at each of these points, and that's why we'll look at the result set later on, and you'll see there's end A and end B 0.1 through 4 stresses. And so you can, if you want to move these around, there is the option to. You've got these buttons down here. You can shift them if for some reason you're really interested in the stresses along the center line at the bottom. But most of the time, we just leave them at the default orientation. We've also got all of your beam properties here, updated live as soon as you change your height or width. If we make this taller, we've got all of our moments of inertia changes, our polar inertia changes, everything updates live, which is pretty handy to see what your beam's doing. If you need to dump this information into a report, we've got these buttons down here at the bottom. You can copy you can copy the text with the button on the left, or you can save this property or section properties as an image to drop into a report. So that's our beam definition here. We'll go ahead and accept that. All of the same information that was shown in the previous pane is right here. If you want to change any of it manually, you can update that. But let's go ahead and leave this at default. And we'll cancel out of that. So we've got our property. Let's add our beam element. And we'll choose our beam property and go from node 1 to node 2. So we've got our nodes selected. Now we need to choose our orientation. If you have an extra node around that you can choose, you can select that node to orient your beam. That'll just draw a vector from your beam end A to your whatever that node that you select is. I generally just grab a vector though, and I'm gonna make my beam Y direction line up with my global Z axis. So I'm just gonna go in here and put a unit vector in the Z direction. We'll leave everything else default and hit OK. So here's our beam. It looks right. We've got a 1/4 inch height, 2 inches wide. You can always go up here into your view options and turn on and off thickness. If you have a ton of beams and it's a little overwhelming, you can play around with that. So let's go ahead and analyze this thing. We've got our constraints. We've got our force. It's fixed on one end, 100-pound force on the other end. We'll do our analysis and analyze. It's a one element model, so it runs pretty quickly. And let's go ahead and contour our stresses, or contour our trend. Now let's do our stresses. So we'll go over here to our post-processing toolbox. And we've got our case one. Let's contour. So actually, let's take a second to look at what these output vectors are. As we talked about earlier, we've got results for end A and end B for each of these output vectors. You can see plane one moment on each end. We've got shear force in plane 1 and plane 2, axial force at end A and end B. On these, on beams, your axial force is going to be the same on your end A and your end B. So let's look at down here. Oh, as we mentioned earlier, we have our 0.1 through 4 combined stress for each end, but we just want to look at our max combined stress. So let's go ahead and look at end B max combined stress. And on here, so our max stress is at the base, which makes sense, 2,400 psi. Okay, that's, or 24,000 psi. Seems reasonable enough. And one cool tool that we have here to use with beams is we can, let's say we want to look at what the stresses are doing in the actual cross-section of the beam, because this isn't super descriptive. The stresses are going to change from the top to the bottom of our beam element here. There's a tool, pretty interesting tool up in View, Advanced Post, and Beam Cross-Section. And we've got our output selected. Let's go ahead and choose our beam element, and let's contour von Mises stress. And if we zoom in here, we can see that, oh no, I jumped ahead here. So what I'm noticing here is our von Mises stress is up around 33,000 psi, which is different than what our max combined stress was. And that's because I've ran it with our other force here. So I'm going to go ahead and rerun our analysis with the right boundary conditions. So bear with me here for a second. And while this is running, just to make a note, we've also got our senior staff engineer, Adrian Jensen, who's going to be manning the keyboards and answering any questions. So see if you can stump him on your questions that you enter here.
Yeah. Send them my way. We don't have any questions yet, but I'll try and keep up. And I'll also keep myself muted. I've got some serious Northwest allergies going on right now, so... Kyle, you're in charge on this one, but I got backup.
All right, perfect. Okay. Oops. So let's look at this again. Moment and force, and we've just got our force output set. Man, doing things live is dangerous. All right, so we're going to contour our force only, and we notice our max combined stress is at 24,000 psi. And we'll go up in here to our advanced post, beam cross-section, and our von Mises stress on our beam element at the end is 24,000 psi also. So our von Mises matches with our max combined stress. And so that's interesting. That makes sense. Okay, so if we want our von Mises and our beam elements, we can just contour our max stress and call that our von Mises, or it's comparable to our von Mises. The area that this gets dangerous is, let's say your system has torsion in it. So something like this, we have our 100-pound force downward still, but then let's say we have a 500-pound or inch-pound moment twisting axially. So it's 500 inch-pounds of torsion on the beam. When we go in here and contour our moment and our force, nothing changes. You can, as we switch back and forth between our moment and force and our just force, we're seeing our max combined stress at 24,000 pounds unchanged. It's not until we go into our advanced post beam cross section that we can see our force 24,000 psi, but our moment and force, we jumped up to 33,000 psi. So you've got to be careful if you have torsion in your elements. Your max combined stress isn't going to show the true stresses that you're really seeing there. And you'll need to go in here to your advanced post menu to really see what the stresses are in that cross section. Okay, so we'll jump back over here for a second. We've got this presentation is going to be uploaded on our website afterwards. You can see there's a lot more text and a little bit more detail in these images, so you can definitely check that out afterwards. Another note on torsion: if you've got a thin-walled open section beam, you have to be really careful with, or really extra careful with torsion. These beams are a lot more susceptible to twisting. When you generate a beam or open section beam in Femap, you'll notice it doesn't line up the beam through the geometric center as you'd expect, but it does this neutral axis offset, which puts all the loads and stuff through the shear center of the beam instead of the centroid. And the shear center is going to be the point where you load your beam and don't get any twisting. And you might think, oh, well, I have my beam's not actually offset like that. I'm going to change my neutral axis offset and line up the beam correctly. It's still going to apply the force through your shear center, no matter what you have selected in your neutral axis offset. So you're going to be, if your force is applied directly to that node and you're expecting it to twist the beam, that won't happen when you're doing the analysis with this. You'll have to manually create a rigid element and offset your force, but in that situation, plate elements might be more appropriate for your beam anyways. A little note on here is if you're using your shear axis offset in nonlinear analysis, you may get some funky results, so definitely try to avoid that. All right, so to summarize the introduction here, some of our limitations, or elements with torsional stresses, that can be a little scary. Nonlinear analysis, not the most reliable if you have a neutral axis offset. But in general, if you have like long, slender bodies, I've heard a 10-to-1 ratio of length to width is a good rule of thumb. If you've got bolted connections, we'll get into those on the next model. They work excellent for that. First pass analysis for just sizing or geometry changes. The way with the beam definition dialog, or definition dialog, you can easily change the beam sizing and experiment with different sizes and weights and everything of your beams. And definitely keep in mind if your structure has low torsion, beams can work great for you. So let's look at some bolted constraints. We're going to get into something a little more exciting now. We've got this pressure vessel. It's all meshed. We've got our boundary conditions. We've got a force over here. I think that's somebody yanking on the valve flange there. And so we've got, these parts are separated. We need to bolt them together. A common way for doing bolted connections is to add a multi-point constraint, so RBE2 on the edge of the hole, create an RBE2 over here, create a rigid element over here, create a beam element connecting the two. That's a lot of clicks, especially as your number of bolts increases. So there's actually a pretty handy API up here. If we go to our custom tools, meshing, and then hole-to-hole fastener, we get this dialog box, entity selection, select the curves at the fastener bottom. So we'll go ahead and select our curves at our fastener bottom, right there, and then select curves at the top hole. All right, we've selected our new holes, our new curve. Okay, and boom, we have our rigid element at the base, we have our rigid element at the top, and we've got a beam element connecting the two. Now you'll notice we never actually, we never defined the thickness of that beam there. It just dropped in a new beam. Like, how does it know what thickness to make it? Well, this API actually goes in and measures our, oh man, which one is it? It actually goes in and measures the diameter of the curves that you selected, and it selects your beam radius based on that diameter. So we've got, these holes are 0.75 inches diameter, and so it made our radius half that. So that's pretty handy. And you can quickly go through and create all of your beams. I'm going to go ahead and open up another model that has our beams already in there, so you don't have to sit and watch me click 100 times. Cool. So here we go. Voila. We've got our 6 bolts through there. We can turn on our thickness just to see what it looks like. We've got a bolted flange. We've got a bunch of bolts through there. Looks pretty good. So let's make sure we have our boundary conditions set correctly this time. We've got a force on that flange. We've got our fixed constraints down there. And we can go ahead and analyze our nozzle load. All right, looks like we got our results. And let's just contour our, overall the model looks like we've got a reasonable stresses, we've got our forces down here, everything looks good. So let's take a look at some of our beam forces. Let's say we want to know what our beams or bolt sizing should be for this flange here. Right now we've got 3/8 diameter bolts, and I don't know if that's really necessary. We can go in here and there's a new function in 11.3, which I think is, I was so happy when I found out about this. It's called contour arrows. And oh man, it looks, if you don't have it set up correctly, it can be kind of a mess. I'm going to go ahead and turn off our thickness. The reason it looks pretty crazy is because we've got our plate stress output vector selected. We're going to go in here. We're really interested in our axial and shear forces on the bolts. So let's go and select our beam axial force. Okay, that looks a little bit more manageable. And notice what happens when we select our beam axial force over here. I'll make this a little bigger so it's easier to see. When we selected that, so we now have our these three output vectors selected. We've got our end A axial force, our plane 1 shear force, and our plane 2 shear force. And then when we go into our arrow display mode, it shows that it shows two separate values. There's the axial force on the bolt and our shear force, and that's combined shear. So this is really what we want when we're looking at like bolt sizing. We want to know what's the axial force on the bolt and what is the shear force. And we can zoom in a little bit and see we've got 300 pounds shear, 500 pounds axial. Perfect. Now, this looks good. It makes sense. This may not be the most conducive to writing reports. If you drop a screenshot of this into a report, a client might not be very happy. So one of the next steps here would be, how do I get this information into a table format? I want to drop this into an Excel doc. I want to drop it and do some bolt sizing calculations, or I want to just drop the forces into a report. There is a pretty handy way to do that, actually. So first we want to use so we're going to use the data table to export these forces. And if you've never used the data table before, it's up here in Tools and Data Table. You have to turn it on before you start, so it knows that it's ready to go. And the next step, we're going to go, so I guess before we get into this, so you want to make sure that you have your shear and axial forces contoured on your bolts. The data table is going to export whatever you have contoured. So first we make sure everything's contoured properly. Then we go Tools, Data Table, turn that thing on. Next up, we're going to select List, Output, and then Contoured Results to Data Table. And sure, we want to unlock our data table. And here we go. We've got our element IDs, we've got our axial force, and we've got our shear force. If you can take these values, and if you want to save it to something you can use outside of Femap, just click this little save button up here and choose your CSV file and bolts. From there, you have your forces. You can use whatever calculations you use internally to determine the stresses and sizing required for those bolts. This one, I did this manually in 11.2 before, about a week before they released 11.3, and I was pretty happy when I saw that one in 11.3 because it saves a couple hours every time. All right, so that's our bolted connections. We've got bolt forces. We've got a little bit of API action. Next up, let's play around with some linkages. We've got this handy model up here, big farm equipment, a bunch of mass hanging out. And let's say you had a new engineer and summer intern that built up this model. It's pretty good meshing, pretty good quality, everything looks good. They drop off the model with you and say, it's good to go. Go ahead and run the analysis. So you believe them, but you want to check the model. And one of the, let's say that these beams down here in yellow are looking overstressed, and you're not really sure why. So we're going to go ahead and we'll turn off our thickness so we can see what the elements look like. Let's start off by putting some Freebody diagrams on this beam. I want to see what's the force in each direction, what's our moment in each direction, what's really happening over here. So we're going to create our Freebody, new Freebody diagram. This will be yellow beam. We'll go ahead and turn off everything except for peripheral elements. And sure, we want to see our forces and all of those. We're going to go ahead and turn off our total force. We just want to see our nodal forces. So, okay, done. And for our free body diagram, we're going to select our element that we want, which is our beam. And we'll select our node that we want our free body forces at. So we'll select that node at the end there. Okay, and no, we don't want our total summation vector. And we do not have our forces here. Oh no, Adrian. We have a hiding free body diagram.
We request all the output we needed.
We should have. So let's see. We've got our equation force and our force balance. So we definitely requested it. We've got our output set selected. Interface load. Oh, we just needed to click on interface load.
There we go. Glad I could help.
Oh man. All right. It's like there is no reason this shouldn't work right now. Yeah, so some of the visualization stuff can get a little crazy.
For anyone that's using free body diagrams or has seen any of our seminars, you just know there's always a little bit of struggle, and of course when you've got 100 people watching, it's just that much more exciting.
We're just trying to show you guys live troubleshooting. Most value
exactly.
possible.
This isn't a demo. This is real modeling.
So let's start off looking at our forces on this node here. We've got forces in the X, Y, and Z direction. That seems reasonable. This thing's got a ton of weight moving around, or that's sitting on it. And looking at the moments, we've got moments about the Z-axis, moments about the Y-axis, and moments about the X-axis. And if this thing is if we want this thing to rotate, sitting in some bearings in real life, there really shouldn't be a moment about the x-axis. So based on that, you need to do a little bit more investigation into what this summer intern did in the modeling, because there should not be a moment in this area. So based on previous experience, you probably have an idea of they didn't release the beam ends. So this, instead of acting as a beam in a bearing right here, it's acting as if that beam was all just welded together at the end. And obviously that's going to generate a moment about that. So how do we release that beam end? We're going to go up to modify, update element, and beam bar releases. It gives you the option to choose your elements to update. We'll go ahead and select this element. And up here we have our end A, end B, and 6 degrees of freedom in our options. It gets a little, I don't know, it can be a little unintuitive at first, but what you're really doing here is you're selecting the end and which degree of freedom you want to let this beam move in. So, and it's also important to remember, beams have their own local axis system. And so the x direction runs down the length of the beam, and in this model it just happens to line up with the global coordinate system. And so for this one, we want to release our rotation about the x-axis. We want it to be able to rotate as if it were sitting in a bearing. But we have two options, end A and end B. One of them is over on the left side, one of them is over next to this big chunky thing. And we didn't model this, so we don't know which element or which node our summer intern selected first. And so we could go in here and click one, and then go and run our results, see how the moments are. But there's a better way. We want to know what we're doing instead of just clicking buttons in Femap. So I'm going to cancel out of this right now, and go up here to View, options. There's also a shortcut F6 to get in here. And then we'll click up on our labels and element directions here. This is a pretty handy way to tell what end is A and what end is B in all of your beam elements. And I just leave it at our default. We've got some options selected, but we just need to click this box up in the top right to say show direction, and we'll hit apply. And I think my performance graphics are messing with me here this morning. I shouldn't have changed anything.
Yeah, for people that are using newer versions of Femap and you have this option for performance graphics, there's a few things that they're still trying to catch up here, the support of filled edges and a few other things. And you need to have the most up-to-date video card. So if you guys do have any weird issues with view settings or visualization, feel free to send us an email. We can help out.
Yeah, I thought it looked better with the performance graphics turned on, but didn't test any or didn't run through all of this with that turned on. So with default settings, when I go up here and choose labels, element directions, show direction, we have our little arrows at the end of our beams. And we can go through here and see all of our beams got these little arrows at the ends. And that arrow is going to show the orientation of our beam. And so the arrow head is at end B, and the wider end is back at point A. And so it kind of points from A to B. So this lets us see what end we want to select in our for our model here. So let's go back to our end release. We're going to go modify, update elements, beam bar end releases. Select our beam element, and that's going to be end A, and we want to release it in the rotation about the beam x-axis. So we'll just select our Rx on end A and select OK. We'll also do the same thing over on this beam. Notice we want it to rotate at this on this side. These two beams are oriented the same, and but the arrow is on the side of the little light blue beams over here. So that's gonna be our end B this time. So go update elements, beam bar releases, select the new beam, and this time we're going to release end B about the Rx direction. Okay. So now we have our two ends released. These beams will be free to rotate in this little corner here and this little corner here. And let's go ahead and reanalyze this thing.
And something I think that's nice when you're working with beam releases is within view options, you can actually turn on, you can have it show the degrees of freedom that are released. Yeah, I think it's a few options, offsets, releases, just the next one down.
Oh. Degrees of freedom.
Yeah, so that's kind of nice. It's hidden behind the Freebody. You can see it on the right-hand side. That's kind of nice because you actually get visual confirmation that it ended up at the right end of the beam.
Very cool. So we've got our results. Let's go ahead and load those things. All right, now we'll select our new output set, and voila, our moment about that x-axis is gone. That makes me feel a lot better about this intern's work. All I needed to do was release the Rx direction, and this thing is behaving like it should. What if we want, instead of using free bodies, there's got to be, like, let's say we want more information besides just the moment about that end of the beam. There's also we can use our advanced post tool again to get even more information about what's going on in this beam. So we'll do view, advanced post, and let's start off with our first result set that has that didn't have the beam end released. I'm going to select the element, and you can see we've already got a pretty cool image there. What we're really interested in is the moment about that beam, or the torque on the beam. So let's turn off everything except for our torque. We can turn on our multiple cross sections. Let's turn on 10. It's going to be cool looking. And let's look at shear. We've got, I don't know, 14. I actually don't know what unit system this model's in. So we can see our stress contours. We've got high stresses, or high Y shear stress due to torque in that direction. And we can scroll through here and see our different stresses. And let's stick with Y shear. Over here on the output set selection, you can choose the case where we had our beam ends released, and you'll notice there is no stress due to the torque in the Y shear direction, and there shouldn't be any for any of these stress selections, because there is no moment about that. There's no torque. We can go back and compare those again. So this gives you a lot more information about where the stresses are in your beam. Let's say you wanted to attach I don't know, some reinforcement onto the outside or something. You can see where your stresses are, and you can see what those stresses are. This gives some pretty cool visualization options. If instead of putting 10 contours through the middle of that, you can just put 1 and slide it down your beam length, which is pretty cool looking. And let's say you just wanted to view your the planar stresses instead of viewing it on the model. You can select screen space, and it'll show you the you can move throughout it, but since it's equivalent throughout the whole beam, it's not going to change any. But that gives you your full field stresses in a pretty interesting method there. All right. So we've got, let me just run through here. So that was everything that was planned for our beams here. Adrian, is there any questions that we can dive deeper into?
Yeah, so let me just take a quick check here. We've got our coordinate systems, we've got our output vectors, cross-section tool, new contour arrows, all that good stuff. I think a lot of the questions coming from the audience were focused around, the difference between max combined stress, which you can contour over your full model of beam elements, versus looking at a true von Mises or major principal stress in the cross-section tool. So if we go back to earlier in the seminar, the max combine is just your axial, your shear, and your bending, no torque, and it's just adding them together, so you can actually get positive and negative values. If you have a beam under compression, you'll see negative max combined stress values, whereas you're seeing different numbers in the cross-section tool because you're actually calculating von Mises, major principal, minor principal, or shear. So it's a totally different output vector, and it's calculated differently. It's kind of depends on what you're trying to get after. Just absolute maximum magnitude of stress, maybe von Mises is the way to go. If you want to see the difference between tensile and compressive, you can use max combine and have those show up. So there's different output vectors, and you just use them for different applications. Sometimes you're worried about stress, sometimes you're worried about compressive axial force in the case of buckling. So it kind of is situational dependent, but it is all using the same force information, same stress calculations. It just depends on which output vector you want. The other questions I see here is about the API, setting a specific bolt diameter. So there's definitely a handful of different APIs out there for creating these bolted connections. This one is really quick and easy because it measures the diameter off of the geometry, but if you want to manually set up a property and specify the diameter, there's other APIs for that. So you can check out our the Applied website. We've got an API section there, and people have taken those, modified them to be, meet their specific needs. So this one was really quick and easy, but if you want a bit more control, there's different APIs that allow for that as well.
Yeah, and one thing to note with this API is you can also go in here and edit your property and change your shape, and you can input any bolt size you want. So if it all depends where you want to spend your time. You can generate all your bolts and then transition I don't know, one size of bolts to property 1 and then transition a different size of bolts to property 2 and then just manually go in here into your properties and change those sizes. One thing that I wanted to touch on that I think is really cool, but there wasn't a great spot to talk about it in this seminar is, I'm just going to go in here and make our beam some arbitrary properties. Over here in the model info tree, one of the updates in 11.3 that I got very excited about was in these property, the beam logos have been updated. So now if you have a rod, it shows up as a solid element. If you've got a Z section, it shows up as a Z section. Even our, I don't know, let's pick some more fun ones. Our rectangular tube gets a rectangular tube logo. So it's just kind of a fun little changes that can be pretty helpful.
Excellent. Yeah, it is those little things that after you've been using the program for a while, it's like, hey, look at that. That's nice. I'm saving time. All right, so we've got some more questions coming in here, but we're approaching our 50-minute mark. So what we'll probably do, if you guys didn't get your questions covered, we'll follow up by email. And a lot of times in some of these seminars, maybe before we upload the presentation that Kyle put together, is we could put a section at the end with frequently asked questions for beams. One of the things that I always suggest to everyone is if you're having questions and you're not really sure how it's working, before you incorporate these techniques into a large model with high repercussions, build a test model. You can learn so much from a 1 or 2 element model, comparing beams versus plates or solids and the way they're calculating stresses. And it's really the best way to go, rather than taking someone's word for it. Is either prove it to yourself with the test model, dig into the documentation, and that way you don't really have anyone else to blame, because you know what's going on, you've proven it to yourself, and you can defend your results. So that's my main plug there, is work with the simple models and really get a good grasp. I think that's how Kyle and I learned a lot of the stuff we talked about here today, is just break it down.
And also between that, or simple test models, and the Femap internal help documentation is great. And a lot of this information today came from the Nastran help files. There's a element guide and a theory manual, and there's the basic Nastran guide that have more information than you'd ever need to know about these elements. So if you're really interested in learning the nitty-gritty details of your beam elements, definitely check those out.
Excellent. All right, thanks, Cal.
Thanks, Adrian. Thanks, Eric.
Thanks, everyone, for attending.